So we are very happy to have Professor Murat Kocaoglu over here, who is an assistant professor in Purdue University. Murat graduated with his PhD from UT Austin, and he was one of the star students of Professor Alex Dimakis, who gave a talk in this forum a few months back, and Professor Sriram Vishwanath. After graduating, he was a staff member at the IBM AI Lab, MIT IBM AI Lab in Cambridge for a couple of years. And then he came back to academia and became an assistant professor in Purdue. His interest mostly is in causal inference and causal discovery, and in general, the causality aspects of machine learning. And I know that in heart, he is also an information theorist. So Murat, the virtual floor is all yours. Thanks a lot for coming.
Thank you, Ari, for the kind introduction, and thank you for the invite as well. So I'll share my screen. I think I have the ability to do that, right? Yeah. Can you see my screen?
Yes, I can see your screen. Looks all good.
Okay. All right. So again, thank you for the invitation. As Arya mentioned, my name is Murat Kocaoglu. I'm from Purdue, ECE, and today I'll talk about causal discovery for root cause analysis. Here's an outline of the talk. Essentially, half of this talk will be about background and a basic introduction to probabilistic causation, then to causal discovery, and we'll talk about Purdue calculus rules a little bit. And then I'll talk about two contributions. One is learning from experimental data, learning causal structures from experimental data. And then finally, an application of that onto root cause analysis among microservices. Okay, so if there are any questions, please feel free to interrupt and just ask. I would like to keep it interactive if possible, so that will be great. So let's start. Okay, so first, before we talk about causality and causal discovery and all that, we need to first define what causation means. That's specifically what's probabilistic causation. So here, let's work out this example. Let's say I have two random variables. Let's say X represents the percentage of population who has access to clean water. And then let's say Y represents the child mortality in numbers. Okay, so you might even have a data set from the UN website like this, where each row, of course, represents a different country. Now, if you ask the question, which variable do you think causes the other one, right? What would you think? So if you know how the word works, you probably will think that X should be causing Y, right? Let me put it in this little graph here. But what does that really mean? So how do we know this should be the case? So if X causes Y, perhaps I can say that maybe Y can be written as a function of X, maybe with some unobserved source of randomness that I cannot take into account, right? But still, this is an algebraic equation. So I might even invert this algebraic equation sometimes, right? So how do I know X causes Y here? Still, it doesn't say anything about that. Right? So to understand what causation means, we need to imagine a thought experiment where suppose I have access to a magic wand, okay? And I'm going to use my magic wand to do some good, and I'm going to force X to take the value of 100. So what does that mean? That means I'm imagining a hypothetical universe where everybody has access to clean water. Okay. So right now we are not questioning the feasibility of this experiment. We are not even questioning how I could have done this, right? Just imagine somehow I was able to set X to 100. Then we ask ourselves, do I expect to see different numbers for Y, different distribution for Y, right? In this case, child mortality numbers. And we know, again, from how the word works, probably those numbers will go down, right? So this is how you would assess whether X causes Y. So we say X causes Y if intervening or forcing a change on a variable change the distribution of the variable Y, okay? So now, what we can do is, if we know this kind of qualitative information that X causes Y, Y causes Z, etc., I can represent them compactly in the form of a directed graph. Right? For example, here, I have 5 random variables. Each one is a vertex of my graph. And I have edges that actually capture this qualitative information. Okay. So when I put a causal structure like this, I will call this a causal graph. And then this will essentially mean that each variable can be written as a function of its parent set in the graph and some exogenous randomness that I don't get to observe. Okay. So this is going to be the assumption that we'll be making. But of course, this is not it, right? This is not all there is. I'm also making assumptions about interventions here. So let's see what happens there. If I have a causal graph like this, which is simply a direct stochastic graph, right? How can I assess the effect of an intervention? So here, again, each variable is generated through a set of structural equations, which essentially gives me a joint distribution between them, right? So the set of equations induce a joint distribution between observed variables. This is called the observational distribution. Now, suppose I would like to intervene on X4. Okay. So this operation is also shown by, is represented by the do operator of per. And let's say I would like to set X4 to the value of 1. Right? So what does that mean exactly? Now, when I again use my magic wand here and set X4 to take the value of 1. One thing to notice is this. Before, the value of X4 was being determined by its parent set. In this case, X1, X2, X3. But now with my intervention, I'm forcing a certain value on X4. So it's no longer being determined by its parent set. So if I would like to represent the new causal relations in the system after the intervention, I need to remove these edges that go into X4. Right? So how would you mathematically represent this? Is essentially wherever you see X4 in the structural equations, you replace that with the value that you intervened on, which in this case is 1. Okay. Now you can see that I have a new set of structural equations, and these structural equations will induce a different distribution between the remaining variables. So this is called the interventional distribution, in this case between X1, X2, X3, X5, given I intervene on X4 and force it to take the value of 1. Okay, so this is Pearl's model of causation, intervention, and the effect of an intervention. As you can see, it changes structural equations, it changes the graph. So these are going to be important later on. Okay. So you can also force X4 to take the value of a different random variable, right? This could come in handy. You just say that X4 should take the values of R. So I'm essentially forcing X4 to be R in this case. And one assumption here we will be making is that R is independent from the exogenous factors that affect other variables. Okay, so that will be useful. All right, so similarly, now I have a joint distribution. Still, this is called an interventional distribution. So this is called a stochastic intervention when I set it to take the value of a random variable. Okay. Let's talk about causal discovery. Now, one thing that we have going on for us is that causal graphs imply dependency models. So what does that mean? That means that if I have the causal graph on the left-hand side here, then it induces certain well-defined conditional independences in my data. Okay, so for example, here we can read, and we are going to see this briefly. We can read that X1 should be independent from X2, right? And we can also see that X1 should be dependent with X2 if I condition on X4. And also, I'll just skip to the last one. X1 should be independent from X5 given X3 and X4. Okay. So essentially, causal direct statistical graph, causal DAG is a Bayesian network for the induced joint distribution. Okay, so this will be useful. Then what can I do if I would like to learn causal structures from data? I can use condition dependence tests to infer some of the directed edges. Essentially, these are going to be the edges that are common to all the Bayesian networks that would explain the data. Or in other words, all the Bayesian networks that are consistent with the set of independences I observed in my data. Okay, since they are part of all the Bayesian networks, they have to be part of the causal graph as well. So these are the invariant edges that we can learn. let's go through an example. Suppose I have a data set, and this is a made-up data set and graph. But imagine we have this graph where race causes parents' income and zip code. Perhaps you can imagine, due to historical segregation, parents' income causes SAT scores, zip code causes SAT score, and SAT score causes salary. So let's say this is the true causal graph, but it's not known to us. So we'd like to learn this from the data, right? How can we do that? Again, as I described, we can run condition dependence tests. Now, suppose I read that parents' income is independent from zip code given race, but then it becomes dependent if I further condition on the SAT score. So how can I use this for learning the graph? Here is the key observation for that enables causal discovery from data. Suppose I have one of the three graphs on the left-hand side. All of these graphs induce the same conditional independence pattern. What that means is that X and Z are dependent variables in this graph, but they become independent if I condition on Y. Okay. You can see that conditioning on Y blocks all of these paths, so they become independent. But if I have this other graph on these three nodes, where X causes Y and Z causes Y, so we have converging arrows at Y. Now the independence pattern reverses. Here, X and Z are independent, but they become dependent conditioned on Y. What can I do with this? I can actually identify all such substructures from data, because I know exactly the pattern that will look like, the pattern that comes from this kind of substructure, and I can reverse engineer this by reading of this kind of pattern, right? So this is the basic idea behind observational causal discovery. So if we go back here to this example, now I have this, this is called unshielded collider. The parents are not adjacent, but we have converging arrows. So now I can learn this from data. Okay. I can learn more things with something called micros because of some constraints. I'm gonna skip that for now. But essentially, this is all I can learn from data. This, as you can see, this is a mixed graph that has some directed edges and some undirected edges. So undirected edges are representing that edge could be either way. There is no way of knowing just by looking at the data. Okay, so this is called an essential graph, and it's essentially a representation of the equivalence class of causal tags that are consistent with the data that I have. Right? Of course, you can use side information perhaps to decide race should not be caused by something, etc. But from data, this is all I can say. Okay. So next question is, why are interventions informative of the causal structure, right? Because we know if you want to assess the causation, let's say whether a vaccine works or not, you would like to do randomized experiments, you would like to perform interventions. So why do you want to do that?
So Murat,
yes.
A very naive question might be, so you just said that some of the causal structure can be revealed by this independence test, whereas some may not be, right?
Yeah, parts of it, yes.
Yes, I see. Okay. So those who can still be confusing after doing all the independence tests, so there needs to be a way to find them as well, right?
Right. So yes, so that's when you stop and ask the question, right? What can I do to proceed? So there are multiple ways. Either you need to put more assumptions, right? You can say something like, oh, maybe I have a linear model. I have an additive noise model, right? I have small entropy, right? Something like that. Then you can proceed. You can learn more things under additional assumptions. Okay. Or you can ask yourself, oh, can I conduct experiments? Now, maybe I'll use some experimental data, either collect new ones, or maybe I have some already, and to learn the rest. But without additional assumptions, without experiments, I cannot go beyond this. That's kind of the statement. There's a footnote there that I'm not opening up, because there are more complicated constraints that you can perhaps read off from the data, but I'm not going into that. So this is all for learning using CI tests. But you can imagine higher order structure arises if you really search for it, but those are hard to find.
Okay.
Yeah, thanks for the question. Okay, so now we are talking about learning with interventions. Let's say we have this structure, right? There's a subgraph of the graph I showed you before. X3 causes X4 causes X5, X3 causes X5. So this is a tournament, fully connected graph. Now, there is no condition dependence that you can read from this graph, right? All variables are dependent and conditioning doesn't change that. This means that you cannot learn any direction. So any total order between these three variables are consistent with my data, okay? Now, this is exactly the setup that I was asking. How do we proceed from here? Suppose now I intervene on X4, right? I collect additional data. I set X4 to a random variable R independent from the exogenous noise. Now suddenly I start seeing new conditional dependencies, right? So this will be informative. Let's see what we can learn. First, I can say that X3 must be the cause of X4, or maybe I should have said X3 must have been the cause of X4, right? So I'm talking about what happens in the unperturbed system by looking at interventional data. Why am I saying this? Because now I can suddenly make X3 and X4 independent, right? So that means there is no edge between them. But clearly there was an edge between them before, and I know the effect of my intervention. The effect of my intervention is to remove the incoming edges, right? So if I put all these three things together, I can reason that, oh, that must mean that X3 must be a parent of X4, not a child, because now I can make it independent, right? So from that, I can reason X3 was the cause. And from the fact that X5 is still dependent with X4, still has an edge, I can reason X5 must be the effect, a child of X4, right? So I can learn the neighbors of the intervened node just like this. I can learn more. I can actually infer that X3 causes X5. And the reason for this is that in the new data that I collect, the interventional data that I collect, I now have an unshielded collider, as I mentioned. So I can learn the pattern from this unshielded collider. X3 and X4 are independent. They become dependent after conditioning on X5 in the interventional data. So I can actually learn this whole thing, and I can actually learn the full graph, as you can imagine, just by using a single intervention. Okay, so from nothing to the full graph. Okay, let me know if there are other questions, any questions around this idea. Okay, so all the cases I discussed so far are sort of like the basic setup where you don't have any unobserved confounders, right? Much easier to explain, but in general, you will have latent confounders. So then, essentially, Peirce do calculus comes into play. So, and for that, I need to talk about what causal inference means. So, oops, sorry. So by causal inference, we mean the following. Suppose I just have observational data, and I know the causal structure, right? Somebody told me the causal structure. Then it's possible to estimate the interventional distributions from the observational data and the causal graph, okay? Sometimes. So this is done through the do calculus rules that essentially gives you a way to convert an interventional query, let's say some do distribution, P of y given do x, let's say, into a function of the observed distribution. And there's a bold if possible here because it's not always possible, but sometimes it is, depending on the graph structure. So we have a sound and complete identification algorithm due to Spitzer and Pearl from 2008 for this problem. So that's what I'm going to discuss next. What are Peirce do calculus rules? Before I move on to explaining how we are actually using them. Okay, so example 1. Suppose this is my causal graph. Notation here is that U is an unobserved variable. So it's an unobserved confounding variable that affects both X and Y. What does it mean for it to be unobserved? It means I cannot condition on it. I cannot observe it. But I know it's there. I know it creates this kind of confounding, right? Because I know the causal graph by assumption. Now, let's try to understand what does this operation do operation do, compared to conditioning, right? Conditioning is something that everybody is familiar with, but this is less familiar to everyone, I believe. So let's try to compare the two. If I condition on X here in this graph, right? I can see that conditioning on X affects the posterior distribution of this confounding variable u, right? Which in turn affects other variables down the line. But intervening on x does not actually affect u, because remember, when I intervene, I'm essentially putting x wherever I see x in the structural equations. The structural equation of u does not have x. None of the ancestors of u have x in their structural equations. So intervening on x does not affect u at all, right? So this is the main difference between conditioning and intervening. If there is incoming edge, all those variables that are upstream of that variable are going to be affected by conditioning, but not so much by intervening. Then the natural question is, when are the two identical? So we say that if there is no active vector paths, so vector path means the paths that start with an incoming arrow to the intervene variable. If there is no such active path to the target, then conditioning and intervening must be the same thing, because they both replace structural equations, and then I got rid of the posterior update issue that conditioning has, right? So, and by active vector path, I mean in terms of d-separation. So for example, here, there is a vector path from x to z, right? So I can go to u, go to y, go to z, but I'm going through the so-called unshielded collider here, and that's actually going to block this path. So this I can check by modifying the graph. This means I remove the outgoing edges from x, and then I check independence or d-separation in that graph. So this will verify that x and z are d-separated through the vector paths from x. Okay, and that's true in this case. So I can say z given do x is the same as z given x in this graph. Okay, so suddenly I can convert an interventional distribution to an observational distribution. Okay, so I can predict what's going to happen after my intervention, so I don't have to perform that experiment, right? That's very useful. So this is one rule of PER, basic version of it. Let's see another example. The next question is, when can I assess that an intervention should have no effect? Right? So I have x given do z as the query here. The question is, can I just remove this do z? I don't want a condition. I just want to get rid of it, right? When is this the same as p of x, essentially? And similarly here, I will argue that if the connecting paths are only true vector paths this time, right? Because if there is a connecting path to the target from the intervene node through the downstream paths, then it's going to affect that, because it's going to affect the structural equation of the child, all the way to the target variable. But if the effect is only through vector paths, I'm okay, because intervening does not change that, right? So here, this is how I assess that. I look at the graph where I remove the incoming edges to z. This will help me assess whether there's a deconnecting path through outgoing edges from z to x. If I read this independence d-separation statement, then I can assess that, yes, the do operation intervention does not do anything. So this interventional distribution is the same as, this interventional distribution is the same as just p of x, right? As if I did not perform that intervention. Okay, so this is the second rule. Actually, that's the third rule. So this first one was the second rule. This is the third rule of PER. We'll see that. Another example, right? So now I'm going to do something more complicated. Let's say I ask the question, what's p of y given do z? Now, let's try the things we learned. Can I just drop do z from here? Not really, right? Because z causes y. So z has some causal effect on y. I cannot just drop that. Okay, what else did I learn? I learned maybe I can just condition instead of do. Can I do that here? Not really, because conditioning on z affects x, posterior of x, which affects posterior of u, which affects y. So I cannot just change my do operator to a conditioning in this graph for this query. So should I give up? Does this mean I need interventional data? Not really, not always. It's more complicated than that. So what we can do here is the following very nice idea. We can actually block the path to y, the vector path to y, by conditioning on x. So if I somehow could condition on x, that would shield off the effect of posterior update of z to U, right? Therefore, I would be able to essentially remove all the backdoor paths, sort of reduce intervention to conditioning. Okay, so let's see how to do that. First, I can start by marginalizing out X, right? I will add X and marginalize it out like this. This is fine because given do, this is simply just a joint distribution. So I can perform any joint distribution operation on this. So I can add and remove X. Right? Now I can see something. In the first term, I see that conditioned on X, there is no backdoor from Z to Y, right? So then conditioned on X already, further intervening on Z is the same as conditioning on Z, okay? So with X in the picture here in the conditioning, I can actually convert do Z to conditioning on Z. The second term is even simpler. This is X given do Z, but I know Z has no causal effect on X, right? So this is nothing but P of X. So what did I do here? I simply converted an interventional distribution into a function of observed distribution, observational distribution. Okay, just like this. This is called the backdoor adjustment. You may have heard the name, right? This is one of the most basic causal inference problems. In general, these are Purdue's calculus rules from his 95 paper. Essentially, it's more complicated than I described, but for the most general case, but the basic idea is essentially this, right? Okay, so that's all for do calculus, at least for us. Now, next, I'm going to talk about learning from experimental data, and then I'm going to talk about the application root cause analysis. Okay, any other questions so far? Okay, so hopefully it's all clear. Let's see our problem setting. Okay. Now, for this problem, we have observational data, but also some interventional data. Suppose some scientists have already collected some interventional data before us for maybe a different purpose. So we have some lying around. We also have lots of observational data typically, right? Now the question is, we want to learn the causal graphs with latent variables. So this is a hard problem. And of course, it's not always possible, right? What we want to do is we would like to make the best use of the data that we have, both observational and interventional, so that we can learn as much as possible, right? So for this, we need to first define an interventional equivalence class for this problem, for this setup. And then we need to propose an algorithm for actually learning it. Okay? So that's what we are going to do. And here's the key idea for this paper. Just like condition independences, just like deseparation in the causal graph implies condition dependencies, right? In the data, the do calculus rules also imply certain constraints on my observations. And now, differently from condition dependence testing, they actually impose constraints across different distributions. So remember, now I don't just have an observational data, single data set. I have observational, intervention 1, intervention 2, intervention 3. I would like to make the best use of all of them. We observe that do calculus rules impose constraints across these distributions. Okay. So then perhaps we can actually use that to reverse engineer parts of the causal graph from data. So that's the basic idea. And this extends the condition dependence-based learning to the interventional setting. For example, reminding you of this graph here, this is the latent variable. Again, U is the latent unobserved. If I detect, let's say, somehow I checked this invariance from my data. P of Z given to X, is that the same as P of Z given X? Of course, when I ask this question, there's always at the end hidden for all X, for all Z, right? Of course, but imagine that's there. If I see this invariance in the data, what does that mean? That means there is no active vector path from X to Z in the original graph. That's structural information right there, right? So can I make good use of that to actually learn the graph from these kinds of invariances? How can I systematically make use of that to learn the graph? So these are the questions we are interested in. Before I proceed, I need to explain a difference between a hard intervention and a soft intervention. So this work is going to be specific to soft interventions. I can talk about challenges with hard interventions if you're interested later, but for us, we'll focus on the soft. So when you say a hard intervention, essentially that removes the incoming edges because you completely destroy the mechanism and you replace the mechanism. In this case, y is generated condition on x, right? You replace it with a marginal distribution that you decide. So there is no more causal edge between x and y. When you perform a soft intervention, you perturb the mechanism, but you don't completely destroy it. What it means is that you still have a conditional distribution, so y is still affected by x, but it's a different distribution, and there is still mutual information between x and y, right? It's not completely independent anymore. So this is called a soft intervention, which is actually more practical for certain scenarios. Let's say you have a drug, you would like to prescribe a drug. The drug's effect will probably not be like a complete removal of edges in the graph, but it will be perturbing certain mechanisms, right? So this is the soft intervention setting. Okay, so we can come up with rules. This is from a different contribution, but we can come up with rules of soft do calculus. It's very similar, so some things need to change. I'm not going to parse this, but essentially you can come up with the corresponding rules of soft do calculus. Now, again, as I said, we are going to use this kind of distribution invariances to infer graphical information. So do calculus rules go from right to left. If this graph constraint holds, then this invariance holds. We'd like to go the other way around, right? So that's called the faithfulness assumption. We're going to be needing that kind of faithfulness assumption here as well. One challenge here is the following. The way Pearl came up with this is, for his purpose, it was sufficient to have this kind of restricted relations between intervention sets. What I mean is, for example, here you see that the intervention is on x and z, but on the right, intervention is on x. Okay. But remember, I'm going to use these to test invariance across arbitrary different interventional distributions. So I may not have a superset and a subset relation between my intervention targets always. So I would need to generalize this to the case where interventions here, the subscripts, are arbitrarily different. P sub I compared with P sub j. Okay, so how do I do that? So that's the first contribution. We extend the do calculus rules to arbitrary sets ij. So now if you read this kind of, so if you have this kind of deseparation statement in the graph, this is very complicated. Don't try to parse it, just to give the basic idea. If you have this kind of deseparation constraint in this modified graph, then this invariance should hold across different interventional distributions. Okay, that's what this says. Okay, so now we are going to talk about the Markov equivalence, right? So we are going to define Markov equivalence between tuples of joint distributions. A tuple of joint distribution is I Markov relative to a graph. Okay, so here I is the collection of intervention targets. So this, all this says is that the invariances that we expect to hold from do calculus rules, they hold in your data. Okay, if that's the case, then we say this distribution is I Markov relative to this causal graph D. Okay, so this forms a collection of distributions that you really cannot tell apart from each other in terms of graph structure. The graph can generate any of them. Okay, so, and then we say two causal graphs, D1, D2, and these have latent variables, by the way, so they are pretty generic. D1, D2 are called I Markov equivalent if the set of distributions that they can induce, right, are identical. So that means if I have access to the tuples of observational and interventional distributions with the prescribed targets, I cannot tell apart these two graphs. It could have come from D1, it could have come from D2. Okay, so this is the notion of equivalence that we are interested in. So one issue here is that these are complicated graph operations, right? It's very hard to reverse engineer what the graph structure looks like from these kinds of constraints. Okay, so for this, we are going to...
a quick
Yes.
question. So even if two graphs are I Markov equivalent, the implication on data or the explanation of data can be completely drastically different, right? So it's not like, so is it interesting to say that, okay, I'm going to give you one of these graphs, or some guarantee such that I'm giving you something which is I Markov equivalent to the actual causal structure. Is that of interest or no?
That is all we can do anyway. Yes. So essentially, what this says is that so this is tied to the learning as well, right? So our learning is based on do calculus rules. So what this says is that if you would like to learn using do calculus invariances, right, you cannot distinguish these graphs. So for our corresponding learning algorithm, this is the right equivalence class, right? Because they can use the same constraints. So
I see.
now
But
you can say,
if I sense in data, like suppose you want to really do, like you have some data set and you want to find out, so giving any one of this, like, is this a good solution, or is this, can it be very different from the actual solution?
No, that is what we are going to do, exactly. Yes. So essentially, the whole point of coming up with this notion of Markov equivalent graph structures, right, is to output this equivalence class.
Okay.
So that's where my job ends, right? So because that's all I can say. So I will just say, okay, given the data that you gave me, here are all the possible causal graphs that are consistent with your data. They can be very different, you're right. But I cannot go beyond that without more assumptions or without more data. So this is sort of drawing that fundamental line that you cannot go beyond in terms of learning using these invariances.
I see. Okay, makes sense. Thanks.
Yeah, thank you. So yeah, so we will see. This will be clear, I think, because I will talk about equivalence class in a minute and how to represent it. Okay, so my last point was that these are complicated graph operations. We cannot really reverse engineer what the graph should look like from these, right? Because each time you look at different data sets, different graph operations come into play. I would like to reason about the original graph. Here, the idea is to actually introduce so-called F nodes. Now, the idea of F node, which is from Pearl's 1995 paper, even in one of his proofs, he used this. So we can represent the effect of an intervention using this extra node called the F node. Right? If I have observational data and if I have interventional data given do X, then I can represent these two together on this augmented graph. So I have F sub X, and I'll say if F sub X equals 0, then I have this observation. This boils down to observational distribution. If F sub X equals 1, this boils down to P sub X, the interventional distribution. So I can combine pairs of data sets together using these binary F nodes. Why is this useful? This is useful because I can actually read off the consequences of do calculus invariances in terms of the augmented graph structure. So what do I mean by that? For example, let's say I read that, and now you can see that fx is actually a random variable, at least in this case. Right? It's a binary variable. It has some joint distribution between everything else because of the way I augmented the data set. So I can read off this independence. Z is independent from fx. Okay. So it turns out this corresponds to checking the following invariance. P of z given do x, this is the shorthand notation for the subscript x. P of z given do x, is it the same as P of x? P of z. And the answer is yes, right? So this is checking rule 3 of Pearl between z given do x and P of z. And similarly, I can read, of course, dependence, the arrow should reverse, etc. So that's the detail. But you can see the implications between these things. So different invariances correspond to now independences or deseparation statements with the F node. Okay, so that structural information I can actually capture using a single graph. Okay, again, this is not general enough for our needs, so we need to generalize. And here is the proposition from the paper. Again, I'm not going to parse it, but essentially this shows that if you have this kind of deseparation in this modified graph, that's equivalent with an if and only if to an deseparation statement in the augmented graph, right? A very specific deseparation statement in the augmented graph that includes these additional nodes called F nodes. So this is useful. So now you can actually see what's happening, right? I introduced nodes so that my problem of learning the graph became very similar to learning the graph in the observational setting. There I have a unique graph. I have independent statements that correspond to these separations. I use that to reverse engineer graph. That's an established problem. By using augmented graphs, it might be possible to do something similar, right? That's where we are going. Of course, not so fast. So with Latents, it's never easy. Here is one thing that we have to add. This is, let's say, the original causal graph. This is the augmented graph with the added F node that represents the data set I have, P and P sub X. Okay. I would like to take a closure of this, an ancestral closure of this. And there's a reason for that, because using independent statements or deseparation statements with latent variables, I can only learn up to the Markov equivalence, which is represented by maximal ancestral graphs. So I'm not going to go into details of what all this means, but essentially MAGs, maximal ancestral graphs, capture the ancestral relations. They keep only one edge between pairs of variables. If Z is an ancestor of Y, I have Z into Y, right? And they are not separable. So you can just for now think of this as a representation of what is learnable using these separation statements about the graph. Okay. The important thing to know here is that the do constraints, do distribution, do calculus invariances, do calculus constraints in A, implied by the graph A, are preserved as deseparation statements in graph B. That's what we showed. And then we can also show those deseparation statements are also preserved in C. Okay. So C is good for our purposes for learning all that's possible to learn from data. Okay, so then we have a learning algorithm. Sorry, before that, we have a theorem that is essentially a characterization of interventional Markov equivalence between different causal graphs. I have D1, D2. I would like to understand whether they will look equivalent to me if I had access to this data set, this data set, this data set. Right? This is called I Markov equivalence. And then here is our characterization. Two DAGs are I Markov equivalent if and only if the maximal ancestral closure, the MAG, of the augmented graphs of them are Markov equivalent. So this is the condition for Markov equivalence, which essentially means that they induce the same deseparation statements. But in our case, we are talking about I Markov equivalence. So D1 and D2 are I Markov equivalent, meaning they can induce the same set of distributions with the constraints that we have. If and only if these structures M1 and M2 are Markov equivalent. Okay. And this can be checked with the existing learning algorithms. So we're going to come to that. Okay, so this is a graphical characterization of interventional Markov equivalence between causal graphs with latent variables. Now, how do we learn these things, right? So that's the next question. I think I'm okay on time. We would like to test do constraints, of course, and these do constraints correspond to the separation statements in our augmented graph or augmented MAG in this case. Now, some of these, what I mean by testable and untestable here is that some of these separation constraints on the augmented MAG are actually testable, meaning they correspond to certain do calculus invariances across your data. But some of them don't. Some of them are just not meaningful. For example, if I had other F nodes here, fx, fy, fc, independence between them don't tell me anything, right? It doesn't correspond to any real test. So there are such untestable deseparation statements, but what we show here is that they don't matter for our equivalence characterization. So we are going to use testable invariances and actually learn as much as we can learn about the augmented MAG from data. So you may have heard of the FCI algorithm. Essentially, FCI is learning maximal ancestral graphs from data, but that only focuses on observational learning. So you just have observational data. You are trying to use CI tests to learn the MAG. Here we are extending that, using it as a base to build on. And then we can actually add an orientation rule here that will allow us to orient more things, because we know more structure about these things. These are not arbitrary mags. These are coming from augmented graphs, right? So we know F node is a source node, for example. It points to things. It doesn't have any parents. So these kinds of side information, we can add this additional rule to make use of those. Okay. So as an example, before I wrap up this section, this was our original causal graph, right? And this is the corresponding mag that we can hope to learn from data. Before the additional rule that we have, if you run FCA algorithm on this, you are going to learn the following augmented PAG. This is called a PAG, partial ancestral graph. The notation here is as follows. Circles represent things that I cannot learn, which means the circle here can be either an arrowhead or a tail. Okay. So the edge between X and Y can be either bidirected, meaning there might be a confounding variable, or it can be X causes Y, which simply means X is an ancestor of Y. Right? So these are very different causal information. If possible, I would like to distinguish them. But FCI can only give you this much. So with the additional orientation rules, we can actually learn that this should be a tail. So in fact, X should be causing Y in the augmented mag, which tells me that in the true causal, in the underlying causal graph, X should be an ancestor of Y, right? So which is true in this case, X goes to W, goes to Y. Okay, so that we can learn. All right, so that was a lot of stuff. So now what if we don't have intervention targets, right? So we have data, but we don't know what intervention was performed. The good thing here is that with our formulation, you can actually learn these intervention targets, because those are going to be the nodes that are adjacent to the F nodes. If I'm also learning the adjacency of F nodes, I can do that, right? If the generative mechanism of X is different between distributions, then F node is not separable in the augmented mag. So this tells us what changed across distributions. This will be useful for the next section. Now, just for this follow-up paper, we can actually come up with an equivalence class characterization based on this. If you don't know intervention targets, you have to be careful. You will have adjacencies of F nodes that will look like these are intervention targets, but that just doesn't mean it's always the case. Because of latents, sometimes you just cannot separate, right? So you will get a superset of intervention targets by checking adjacency of the F nodes. I'm going to talk more about this in a minute. It's not really an issue if you don't have latent variables, and that's what we are going to focus on in the next setting for root cause analysis on microservices. Okay. All right, final section. So we are interested in performing root cause analysis using some of the ideas I described here. What do I mean by RCA? You have a microservice architecture. What does that mean? That means you have a bunch of different pieces of code, and then they all call each other, they all operate across, and then that's a very big system, right? And different people deploy different parts of it, so you don't really know what's going on, right? Something failed. So your system is suddenly not responding. Your website is not loading, right? What went wrong? So this is a real problem. And this is a problem where experts spend hours and hours to actually debug, right? You can lose a lot of income revenue if you are trying to fix a bug to have your website online, right? You don't want to do this. So if possible, we'd like to automate root cause analysis. And for us, that means using causal discovery. How do we do that? Here is the key idea. We are going to, it's actually very simple. So we are going to simply view the anomalous data set. So now we have normal operating data set, and also some flag went up that said something is wrong. After that, we collected interventional data. So we have both observational and, we have both normal and anomalous data. We are simply going to view the anomalous data set as post-interventional data set, right? So something failed means some mechanism changed from the normal operation to the abnormal operation. We can represent this with the F node that I described. So F node pointing to Y means the root cause should be Y because the mechanism of Y has changed from the normal operation to abnormal operation. Okay, and then we can simply use the existing causal discovery algorithm that I just described with unknown intervention targets to sort of recover the adjacencies of the F node that will tell you the what are the intervention targets, and in this case, intervention targets will be the root causes. I will go a little faster than I thought because of time, but essentially it says this shows the relation between, again, a similar idea. If X is independent from F, that means distribution of X did not change from normal operation to abnormal operation state. Similarly here, if Z is independent from F given Y, you can read this from data, then the conditional distribution did not change. Okay, so nothing wrong there. Z is also fine. But when you read Y is not independent from F given X or given Z or given whatever, right? Then you will see that the conditional distribution of Y given X has actually changed, which means that something went wrong with Y, right? So this actually can tell the engineer very quickly, these are the candidate root causes, so perhaps you would like to check this first, right? So that's the idea. So of course, full graph discovery might be redundant for this purpose. And it also takes a lot of time because you have too many CI tests if you have a lot of variables. And we only need to know the root causes. So what we did here is that, can we make the algorithm more efficient? And the answer is yes. We simply applied the following idea. We divided the data into different buckets. Let's say I have X, W, Y, Z. These lie on some ground truth graph where there is some intervention here. So I have two data sets, right? I divide it into two sub data sets, X, W together, Y, Z together. I find the root cause within each, right? So this gives me a candidate set of root causes. I can combine them in phase 2 and run another version of root cause discovery, intervention target discovery, and that will eliminate the wrong one, right? So Y will be eliminated here and X will prevail. The thing is, okay, so that's the algorithm I just described, hierarchical version, way to find root causes. This is not complete. So this is a sound algorithm, meaning that you will always output a set that contains the root cause or root causes, but it may output things that are more than that, right? So it may output a superset. Even without latent variables, this can happen. But this is okay because essentially you are reducing your search space from, let's say, 1,000 variables to 10, and that still saves a lot of time in terms of finding the actual root cause, right? So we have some baseline comparisons. These are existing work. I'm going to just skip these quickly. There is a case study that we did called the SockShop application. Here you can actually mimic interventions and failures, and you can collect data, and it seems to perform really well here. And then finally, we also worked, this is a joint project with Adobe, and we worked with a real data set where we show that our method here called RCD can actually find the root causes quite effectively. If you sort them as the most likely root cause using some heuristic idea, then we get a pretty good job compared to the baseline using this. Okay, so I think I'm good with 3 minutes to spare. So these are related publications about this this talk, and I will take questions if you have any. Thank you so much for listening. Let me know. Oops, no. If there are any questions.
Thanks very much, Murat. Yeah, this was really good. So is there any question from the audience?
Yeah, hello, Murat. May I ask a question? So,
yes, please.
Yeah, thank you for your very interesting presentation. So I wonder, like, when you detect the root cause, you introduce the F node. So do you need that the data set before and also after interventions? So even
yes.
if we don't know the where the intervention is, right?
Yes. So here I'm assuming that somebody gave me, look, this is the data we collected under normal operating conditions. Right? Mm-hmm. That is not difficult. And I'm also assuming somebody gave me, these are the data that are collected after something went wrong. Okay. So,
I see.
So that might look like a restrictive assumption, but what happens in practice is that these companies already have systems in place that raise alarms when something goes wrong. So they can actually detect, something is happening. So now, after that, you can start collecting data. And of course, you don't want to wait too long, but then you can actually collect this kind of data. So that's what I'm assuming, yes.
I see. Thank you. So yeah, in our CDNOT paper, we also rely on the different types of data set in order to detect which variables has a direct edge with the F node. In our paper, actually, we call it C node. Yeah, and now we are wondering, how can we handle it? When we don't know actually, like the labels, which which data set has intervention, which doesn't. Yeah, go ahead.
But you can learn it. So that's the whole point. Right? So if you actually run independence tests, now, okay, let's be more precise, right? So I said some things under the right. If you add all the F nodes, that's not a valid Bayesian network, first of all. So you have to be careful to not treat F nodes as random variables. You have to treat them as parameters. That's one trick. But given that, let's say we just have two data sets, you can conduct independence tests between F node and the rest of the nodes, run the FCI, run the PC, whatever, and that will give you the adjacency, right? So that will give you the intervention targets. This is essentially what we are using. So similar.
Yes, exactly. Yeah, I mean, what if we don't know the F node? So we don't have the values of the F node.
Oh, I see. So you have a mixture of observational and interventional data.
Yeah, it's like more like clustering without the labeling information.
That is difficult. There was a paper in a workshop that we're trying to address that, I think, under certain conditions, but it's in general a difficult problem.
Yeah, because so our CNOT paper like handled this problem some time ago. Now later we also met some other problems when there's no labels.
I see.
Yes,
I see.
So it will be also interesting if we can handle the case when there's no label.
Yeah, that is very interesting. I agree. Yeah.
Thank you.
Let me know if you have a paper on that. We'll be able to check out.
Okay, is there, thanks, Bioid. That's a very interesting question. So is there anyone else who wants to ask anything? If there is nothing, we will thank Murat again, and we'll look forward to seeing you in ITA, where we can discuss this a little more.
Yeah,
thanks,
sounds
Murat.
great. Thank you, Arya. Thanks a lot.